Hello all, we met again, and for today I will discuss some of the problem related to the internal force and internal moment. Okay, and the problem that we will discuss about today is this one. Okay, this particular problem. As you can see, for this particular problem, please ignore all the writing there. Okay, as you can see, for this particular problem, the one that will be a troublesome is this one, this part, because that is not the one that is directly directly in contact with the problem in question. The problem in question is to find the shear force, normal force, and moment diagrams for this particular part, ABC, the straight part of the ABC. Okay, that's why, like it or not, in order to do that, right, we have to transfer all the forces and moment to this particular part, ABC, the straight part of the ABC. The force from member CD, it can be directly, it is directly connected there at point C. The force from pin joint A, it is there already at point A, but the 6 kilonewton force, we have to transfer it to point B. Okay, that's why we have to cut it at this particular point. Okay, the cutting there, after we cut it there, the free body diagram of this particular cut, right, become like this. Okay, there is a 6 kilonewton going down, and then at the cut at B, okay, at the cut at B, there is a external, there is a reaction force F going up and moment going to the counterclockwise. This is all the direction here is based on my assumption. I assume it that way. Okay, then after using sigma, after that we can solve for F and M using sigma Fy and sigma moment. After we calculate that, the F is 6 kilonewton going up, correct? And the moment is 9 kilonewton meter counterclockwise. Okay, then after we calculate this, the next thing that we can do is to transfer all of this calculation to the straight part of ABC. Okay, but remember, whenever we do transfer the things, we have to the direction will be the opposite, because the equilibrium is supposed to be there. That's why this 6 kilonewton meter, if we put it in the main free body diagram, this part, the second free body diagram, this one, if we put it there, you can see the 6 kilonewton meter is supposed to be going down like this, and then the 9 kilonewton meter is supposed to be going counterclockwise instead of clockwise. It's supposed to be going clockwise instead of counterclockwise. That's why now this is our main free body diagram that we're supposed to solve in order to get all the external forces that we need. Okay, as usual, we have three equations: sigma moment, sigma fx, and sigma fy. Sigma moment at point A, what will I get there is there is 6 kilonewton from at point B. So the distance here is 3 meters, and the distance here another 3 meters. So 6 multiplied by 3. So if clockwise is positive, so what I will have is 9 plus 9 kilonewton meter from this one, plus 6 kilonewton meter multiplied by 3 from this one, multiplied by the distance, 3 meters. Okay, the distance here is 3 meters. The distance here is another 3 meters. And then I will have as well plus, sorry, not plus, minus FCD, okay, sin theta, in this case is 45 degrees, multiply by the distance 6 meter equal to 0. Then from this calculation, what will I get is FCD will be equal to 27 divided by 6 multiplied by sine 45 degrees. Yeah. And the value is supposed to be 27 divided by 6 is 4.5. Then divided by sin 45. What will I get there is 6.364 kilonewton. Okay. Then using sigma fx equal to 0, what will I get there? Will be ax plus fcd cos 45 degrees equal to 0. So I will have ax equal to minus fcd cos 45 degrees. In this case, it's supposed to be minus 6.364 multiplied by cos 45 degrees, which is the value is supposed to be 4.5, sorry, 4.5 kilonewton. That's ax. Using sigma fy equal to 0. Okay, going up is positive. What will I get? Ay minus 6 kilonewton plus FCA plus FCD multiplied by cos 45 degrees equal to 0. Okay, so there my ay will be equal to 6 kilonewton minus FCD cos 45. Okay, ay will be 6 minus 4.5, which is the same as 1.5 kilonewton going up. Okay, so this is all the reaction force. Now, I will continue with the next step. After we find out all the external forces, I will continue with the next step of drawing the internal force distribution and internal moment distribution. Okay. Just now, this is all the results. And then I try to draw the new free body diagram, which represent all the correct external forces. It will be like this. Okay. It will be like that. So 4.5 kilonewton, why I divided into 2, just in order to make it simpler. So I divided into FCD cos theta and FCD sin theta. going up is 4.5 kilonewton, and going to the right is 4.5 kilonewton FCD cos theta. Okay, and at the right side, at the left side, just now we get the value of 1.5 kilonewton going up and 4.5 kilonewton going to the left. Okay, now as usual, in order to solve this, the continuity there will only holds from the x equal to 0 until x equal to 3 meters. That's for the first equation. Then because of there is a external concentrated force and moment there, the continuity will not be there anymore. That's why from x equal to 3 meters to x equal to 6 meters, we have to use new equation. So we will have two different equations there. Okay. Now, for the first cut, let's draw the free body diagram. This is this is the free body diagram of the first cut. Okay, we have 1.5 kilonewton going up and 4.5 kilonewton going to the left. Then I draw all the positive direction for V, A, and M. V positive is going down. Okay, A positive is going outwards, and moment is to make it smile like this, M, and this the distance here is supposed to be x. Okay, first that I want to solve is using sigma fx equal to 0. Using sigma fx equal to 0, what will I get there will be, if A is going to the right, if positive is going to the right, not A, this one is not A, sorry. This one is N. Why suddenly I make it as A, N. Okay, this one is N. So N minus 4.5 is equal to 0. So our N is equal to 4.5 kilonewton. Okay, now I can draw at the end there. So this is 4.5 kilonewton. Okay, then using sigma Fy equal to 0 and going down is positive. Okay, what I will get there will be N minus 1.5 kilonewton is equal to 0. Sorry, not N, V. V minus 1.5 kilonewton equal to 0. So V there is supposed to be 1.5 kilonewton positive. Okay, now I can draw there. This is 1.5 kilonewton positive. 1.5 kilonewton. And then the last one, using sigma moment of the right from the right edge equal to 0. What will I get there if counterclockwise is positive? M minus 1.5 kilonewton multiplied by x. Okay, so my M will be, my moment will be equal to 1.5 x, and the unit supposed to be kilonewton meter. Okay, as usual, in order to draw the moment diagram, I try it at M at x equal to 0 and try to find the value. There is supposed to be 0. Then at x equal to 3 meters, I try to find the value as well. Okay, and here 1.5 multiplied by x, so the value of x is supposed to be 4.5 kilonewton meter there. So if I have to draw the moment diagram, it's supposed to be going like this. this is 0, and this is 4.5 kilonewton meter. Then after that, we go to the second cut, because usually for the second cut, we use the right part of the cut. Okay, for today, I will try to use the left part of the cut in order to show you what is the difference using the left and the right. It will be exactly the same. So now the free body diagram become like this: 4.5 kilonewton, 1.5 kilonewton going up, 6 kilonewton, 9 kilonewton meter. Okay, as usual, I will draw all the positive direction for V, N, and M. And the distance here is supposed to be X as well. Okay, now using sigma Fx equal to 0, I will find out that N minus 4.5 kilonewton is equal to 0. So my N is the same as 4.5 kilonewton, which is the same as before. So if I draw the distribution, it will be just constant like that. Now I will go to the second one, using sigma Fy equal to 0. Okay, using sigma Fy equal to 0, what I have there, if going down is positive, V plus 6 kilonewton, okay, minus 1.5 kilonewton equal to 0. Okay, so what I will get there is V equal to minus 4.5 kilonewton. Okay, so here I will draw it like this. Okay, and here is minus 4.5 kilonewton. Now the last one, using sigma moment at the right edge equal to 0. Okay, and counterclockwise is positive. What I will have there is moment, okay, M minus 9 kilonewton meter due to this one. Okay, plus 6 kilonewton multiplied by the distance. The distance is supposed to be, this one is supposed to be X minus 3 meters. Okay, and then from this one, from 1.6 kilonewton, there will be another moment there. The moment is supposed to be negative because it's going clockwise. Negative 1.5 multiplied by X is supposed to be equal to 0. Okay, then I will get the value of M. Okay, the value of M is supposed to be 27 here. Okay, then minus 6x minus 6x plus 1.5x, so it's supposed to be minus 4.5x. Like that. Okay, then if we now we go back to the moment distribution. As usual, in order to find out the moment distribution, I will have to find out the value at moment of at x equal to 3 and at x equal to 6. At x equal to 3, okay, the value is supposed to be 13.5 positive kilonewton meter. Okay, supposed to be roughly here. Then at x equal to 6, it's supposed to be 0. That's why 27 minus 4.5 times 6. Okay, yes, it's correct. 0. So later, my moment diagram will be like this. Okay. So as you can see here, we get all the moment diagram, shear diagram, and normal force diagram. Okay, the normal force will be constant from the beginning until the end, and the value will be 4.5 kilonewton. Okay, the shear force diagram, at the beginning it will be 1.5 kilonewton positive. Then from 3 meters to 6 meters, the value is going to minus, it become minus 4.5 kilonewton. Then for the moment diagram, okay, the value at the beginning is going up, the gradient is positive. The gradient here is positive because the shear force value there is positive. Remember that the moment equation is supposed to be the integration of the shear equation. So the gradient is positive, going up. Then after that, it jumps from 4.5 kilonewton to just now 13.5 kilonewton. So this value is 13.5 kilonewton. Okay, this value is 13.5 kilonewton. Then after that, it's going down. Okay, the jump there, the delta here between this particular point and this particular point, the delta there is supposed to be equal to 9 kilonewton meter. So the difference between 4.5 kilonewton and 13.5 is 9 kilonewton. So there is a positive jump of 9 kilonewton meter. So it's correct, right? So there is a jump there, 9 kilonewton meter. Then after that, the value is going down. Okay, the value is going down. Why it's going down? Because the phi there, the phi there is minus 4.5, and so the gradient is minus as well. Okay, that's why it's going down. Okay, I think that's all for now. Thank you very much for listening. I think that's enough for this particular video.